In this video, I'm going to talk about why the Laplace transform of the convolution of two functions is a product of the Laplace transform of the individual functions themselves. Okay, so let's say we have the convolution of two functions f1t and f2t. This is a convolution of f1t and f2t. That's the definition of a convolution. So it is the integration of 0 to t, f1t minus tau, f2 tau, d tau. That's the convolution of two functions. Let's say I want to compute the Laplace transform of the convolution of two functions. Okay, here we use the definition. So we use the definition of the Laplace transform So it's just integration from 0 to infinity e minus st time whatever function we have and integrate that over t, because that's the definition of the Laplace transform. Okay, now we do a small trick over here. So what happens here is we move this one to this side. So what this means that we can move e minus st to this side. The reason we can move this to the inside integration here, because this is the integration over tau. So because this is not a function, this function of t not a function of tau, so you can consider that as a constant, so you can move it inside. So what we do is move to the inside. So we have integration from 0 to infinity, integration from 0 to t, e minus st, f1 t minus tau, f2 tau, d tau, and dt. Okay, so here's the second trick. Okay, so here's one trick. This is fairly easy to understand. This trick, I want to swap the order integration of d tau and dt. So here is our first integration d tau, then integrate dt. Now the next step, I want to first integrate dt over d tau. Okay. Now the function will be the same, as we see, it doesn't change. Or we switch order, doesn't really matter. It doesn't change anything. The reason we do this switch order, we want to make sure the integrated region will be the same when we do for this two, which means the integration will be the same, right? So this is a double integral. As long as the region that we integrate over, because this is a function, they are the same. As long as the region are the same, so they are the same. They will be the same. Okay. So if you look at this one, the integration region for the first one, so tau is from 0 to t. So tau is from 0 to t, and t is from 0 to infinity. Okay. If you sort of draw like that, if I could draw like that, so I have let's say this is t, right? So t can be 0 from infinity. So t can be anywhere over here. Okay, go to infinity. But my tau has to be less than t, right? Let's say this is tau. Now tau has to be greater than or equal to 0, but less than or equal to t. So it has to be. Suppose this is t is equal to tau. This line. So it has to be somewhere over here. So you have the entire region. Of course, goes to infinity. So you could include this line, goes to infinity. Now if we switch order, I integrate it over dt first, then d tau. What's going to happen is, again, so I want to say, if I integrate over this region, the same region, if I start with tau, so tau can be 0 to infinity, because tau starts with 0. As t goes to infinity, tau can also be infinity. So tau here from 0 to infinity. Now t means t has to be t has to be greater. So now t has to be greater than tau, because this is t less than tau. This is has to be greater than tau. So in this region here, the t has to be greater than or equal to tau, because this line is t equal to tau. For this point, for example, here, this t is larger than tau. So this is t greater than or equal to tau. That's why here t has to be greater than tau, but less than infinity, of course, right? So that's equivalent. That's the two should be equivalent. Okay, it always means the same. This region. Okay, of course it goes to infinity. So which means I do the switch order. I sort of change this. If I integrate over t, the range has to be from tau to infinity, and tau has range from 0 to infinity. Okay, so that's we do the switch order of integration. Okay, once we do that, the next following steps are relatively easy to understand. Okay, once we do that, so next step is we do a split. Okay, we split this e minus st as e minus s t minus tau times e minus s tau. So the reason this is true is because if we do e minus s t minus tau times e minus s tau, which is, I can do the term, is e minus st plus s tau times e minus s tau. You see, this will cancel out, so I have e minus st. So which means it doesn't change. Then I keep the same, okay, I keep the same, okay, the range will be the same, everything else will be the same. Okay, so now what do we do over here is, okay, we sort of integrate this, we put this together, so we do, we shift a little bit, so we shift this e minus st and f2 tau over here, so keep it over here, and then we have put these two together, so e minus st minus e to the minus s times t minus tau and f1 t minus tau, put them together. Now we do a small change of variable. Okay, so this one we have, originally this part should be equal to e minus s t minus tau and times this f1 t minus tau. Okay, now we have defined this new variable called t bar. T bar is t minus tau, so this becomes t bar, so this is t bar, basically this is also t bar. So I have e minus s tau st bar times f1 t bar. This remaining term is just this guy and this guy, they'll be the same. Okay, now of course this guy I can change it to dt to t bar. The reason is the integration outside one I consider tau to be constant when I do the inner integration. So this one you sort of consider tau to be a constant, so dt bar is dt minus tau, because tau is considered constant when you do the inner integration. So this is a dt, which means the same. Okay, once I do that, I sort of can, because this is not a function of t bar, because this function of tau is not a function of t anyway, so I can move this one to the outside of the integration. I can do this, you sort of can consider it as a constant. Okay, so I can move this whole piece outside, okay, because it's not a function of t bar. Now do the inner integration. Now here I have to pay attention to here. The integration originally is tau, the t is integrated from tau to infinity. Now because t bar is t minus tau, remember t is to infinity, so t minus tau, which is t bar over here, has to be greater than 0 and less than infinity. Okay, so that's why integration here becomes 0 to infinity. So 0 to infinity, so keep it here 0 to infinity, and e minus s tau, tau bar, t bar, f1 t bar, and dt bar. So this is the exact definition of f1s. Okay. Alright, so once we do that, so this is f1 of s, so this is not a function of tau apparently, so I can move this one outside. Okay, and then this inner, the remaining term will be integrated from 0 to infinity e minus st f2 tau d tau. So this becomes the Laplace transform of f2t. Okay, so that's why it's the product of f1s times f2s. That shows that the Laplace transform of a convolution of two functions is the product of the convolution, the Laplace transform of individual functions.